super smart and pick this stuff up very quickly. So, oh, and then like I said, reading guide 6, I would normally have you do before, but you guys just take good notes with reading guide 6. It's 13 questions, and it talks a lot about the periods and the elements and the properties. That's something that you'll do tonight. Okay, and these are all related to that. Okay, we're going to talk about these 4 periodic trends. Do not write down these right now, because I have a slide on each of them. But the 4 periodic trends are atomic radius, which you investigated a little bit. Who got to the ionization energy part? A couple people, okay? The ionization energy is really interesting, and these last 2 we should get you today. We'll see how well we do. And I do have a couple of notes, and I will show you it on your, it's like a 4 to a page. You have the quantum notes there. You have the EMS notes there. Find that page if you want it. It's just pretty much got a periodic table on it, and just little pieces of information here and there. I'm going to borrow yours. Looks like that. If you want to see it, there it is right there. I've just got the key vocabulary and some questions we're going to practice on. Okay, so for periodic trends, and they're called periodic trends because they're periodic. There are some exceptions to that, but they're across the periods or down group. This is the big piece of information that you didn't see on your in your reading, in your little investigation you did a second ago. So these 2 factors here, I'm going to scroll down so you can see the next one in just a second. These are the ones you definitely want to write down because you need to know how to use these words appropriately. So factors that cause the trends that we saw. So why in the world is the atomic radius decreasing from left to right? Why? There's a reason, and that reason is called the effective nuclear charge. Okay, make sure you write down. I'm going to be quiet so you guys can write down some of that stuff too. And so I explain it here, but I'm going to explain it some more too. Okay, I'll scroll down just a second. So I'm going to start with effective nuclear charge. What does this phrase mean to you? The effectiveness of the charge of the nucleus. It actually means what it says. There's no funny business here. So if the nucleus is charged, it's strong, high, a lot of protons, then the effectiveness of the nucleus is better. And the effectiveness, though, what are we actually talking about? We're talking about the effectiveness of its attraction to its electrons. We're good with the words. Okay, so let's talk about a bit more. So when we talk about the effective nuclear charge, you have to have a controlled experiment. Anytime you do an experiment or comparison, you have to always have a controlled one. So a lot of times it's hard to compare something on the periodic table up here and then something way down here, because you're changing not only periods, but you're also changing groups, and you're changing a lot of things at once. So when we talk about the periodic trends, I'm talking about either a period factor, meaning across a period, or my next one is shielding effects down a group. So we try to compare it very strategically. So as you go across a period, like we were doing with that example, we had 11 protons for sodium and 18 protons for argon. The effectiveness of sodium on its ring of electrons, its valence ring, is okay. But the effectiveness on these electrons, the same level, same energy level that argon has, is much better. And so I'm drawing them the same, but as that occurs, it can cause the decreased atomic radius due to the fact that it's stronger pull as pulling the electrons in. That's as simple as I can make it for atomic radius. But basically, we're looking at number of protons per energy level. So you don't get to compare different energy levels with this factor. So if you're ever comparing across a period, you always want to say the effective nuclear charge is stronger, the effective nuclear charge is weaker. That's basically how you can explain things based on the effective nuclear charge of the proton number being different across a period. It's very specific. So if I wanted, can I scroll down? Yeah. If I wanted to talk about something down a group, I use a different reason. The reason is called the shielding effect. Or shielding effect is also termed electron shielding. So take a second to write down what you need to there. This is the second factor we use in our explanations of the periodic trends. Okay, so the electron shielding, aka the shielding effect, is you literally should think of a shield, the knight in shining armor. You have a shield. The shield would block you from harm. I just saw The Hobbit, so I'm just thinking about that. But it's blocking you. So if you, being the nucleus, are shielded, then you can't do anything out to the things past your shield, or vice versa. Things can't harm you. So it's really easy to think of it that way, because we have a lot of shielding when we have a lot of energy levels in between myself, the nucleus, and Tyler way back there, my valence electron. So I'm going to explain this right here. So if I'm the nucleus and I have one energy level, Allie, she's my next energy level, and I'm trying to keep her on my atom, then we're really close to each other. There's nothing between us. We can hold hands. I'll never let you go. She's not going to escape the atom. But if we have that, this was my example. Here's Allie. Allie. There you go. And there's me. She's just my little electron out here. But if we're talking about something where we have a nucleus, and then energy level, energy level, energy level, energy level, and then here's Tyler, over here, this last electron. Look at all you people in the middle. I can't even see them. I'm like, Tyler, I don't really care. But you can go react with another element. I got all these guys here. But basically, all of you are blocking me from attracting him with my positive charge. Does that make sense? It's shielding. You guys are shielding me from holding him in place. So he's going to be that crazy electron that does crazy things, that goes and reacts with other things, okay? So do you think it's easier if you were trying to steal my electrons, if you're trying to take them, do you think it's easier to steal Allie from me or Tyler? Definitely Tyler, right? Because he has less attraction to the nucleus, whereas she's really close to the nucleus and more attraction to the nucleus. So it's going to take a lot more energy to steal Allie, because of the attraction component, than Tyler. So that's going to be called ionization energy in just a second. Anyway, you only talk about the shielding effect when you are going down or up a group, because that's the only time you're building or losing energy levels. You never talk about the shielding effect across periods. You talk about what across periods? Atomic radius is going to be related, but what was that factor? Right, effective nuclear charge. Oh, and I didn't tell you. This is how we label that. Effective nuclear charge has a nice abbreviation called ZEF. Why ZEF? Why Z? What does Z mean for the atomic structure? Proton number, right. So Z is the proton number, or the atomic number, right? What do you think this EFF means? Effectiveness. So ZEF is the effective nuclear charge, and so I don't like to write effective nuclear charge, I'll write ZEF. Cool? Cool. Okay, the very last thing I talk about is distance from the nucleus, but we already considered that, talking about Coulomb's law, so I'm going to hit that as we go through some examples. So I'm going to try this. I'm going to try to explain this as simply as possible. Let me get myself a clean page. Versus going through everything individually. Draw yourself a quick periodic table, or draw yourself, or you can use your green periodic table. You can write all over it. It's good. And I want you to, in a second, give me your guns. Throw them up. These are our gang signs we will use in class. Okay. So your right hand is your right hand. Click your right hand. Okay. Right hand radius. Turn it this way. On the board. Okay. Now make a picture with your other hand. You know how to make a picture? Snapshot. Okay. No. Okay. Somebody help a brother out, because I see some weird hands. Right hand this way. Left hand this way. Thumbs are in opposite directions. Make a picture. Yes. Make your picture. Okay, your picture. I think everybody's hands are good. Okay. This is your periodic table, and your fingers are pointing different directions, right? Your fingers pointing different directions represent the increasing and decreasing trends. Okay, so now just your right hand radius. And I made this up for myself when I was your age, so forgive me if it sounds dumb, but I have remembered it since then. The atomic radius increases left and down. So write down, draw on your periodic table, increasing atomic radius, decreasing atomic radius. Your fingers, the way your fingers are pointing, are the increasing nature of the atomic radius. And so I try to be strategic and saying right hand radius. You don't forget it's the right hand that represents how the radius increases and decreases. Okay, so why? Tell me the reasoning why the increasing radius occurs from right to left. Because what? Go for it.
I think it's because the amount of protons
Is
more towards the right.
Okay, so tell me in reference to the left then. Because lower.
Because it goes to the right.
So the proton number is lower on the left, right? So, correct. I can't say right. Increasing atomic radius to the left because there's a lower effective nuclear charge. And how do you get a lower effective nuclear charge? You have lower number of protons. Good. Lower protons.
More protons is
on this side, right? So we're talking about going to the left. Okay?
No, I thought that more protons leads to a higher effective charge.
True story. So lower protons would be a lower effective nuclear charge, right? Right? Okay. So on this side, draw yourself an atom that is larger, and on this side, an atom that is smaller. Just so you have like a clean picture of everything in one here, okay? So that's your right hand you were describing. Your right hand is your radius. Everything else we're going to talk about is your left hand. So your left hand was like this, right? Correct? It went up, your thumb went up, and your finger went to the right. So everything else we're going to talk about trends-wise, the ones that you just saw on the very first slide were ionization energy, electronegativity, and electron affinity. Now, I need to describe what these are before this will make sense. So that's me on the next page. So we'll come back to our drawing, so leave some space on your drawing so you can add some extra notes. So this was ionization energy, electronegativity, and electron affinity. We're going to hit those now. So I'll tell you what I feel is important to write, but after that you guys can kind of do what you need to do for yourself. Okay. So, oops, wrong way. We just talked about this. Do not write this again, but unless you need some time to look here. So we're talking about the atomic radius, the size. Across the period, we knew the nuclear across from left to right, the nuclear charge did what? Increased or decreased? From left to right, the nuclear effective charge increases or decreases?
Increases.
From left to right. So we got to think about what I'm saying. It definitely increases because of an increase in proton number. So what gets, the effective nuclear charge gets greater. That's what that says. So that is the only thing affecting the radius from left to right or right to left, whichever way you're speaking of. Nothing else changes. The distance, technically, the electron distance from the nucleus is now changing because they're in the same energy level. So the energy level is not changing. That's why we ignore that feature, that shielding effect. There's no extra shielding effect from left to right. We're only considering the nuclear effective charge. So nothing else is changing, just the nuclear effective charge, which causes the radius to increase or decrease. There's a bigger positive charge on this side, which means that the radius will then cause, or the charge causes the radius to shrink because of the attractiveness. Okay, so that's just a general atom. Let's talk about ions now. So ions. When you have ions, some things happen. Electrons have been lost or gained, yes? So let's do a really simple one, lithium. Lithium, I'm gonna draw the Li orbital because you know that the Bohr model only works for hydrogen, but I'm gonna draw it so you can see the image of the orbits being lost. So here's lithium. Why do we have 3 electrons? because of three protons, right? And it's just a balanced charge here. So if this is lithium, why did I only put 2 energy levels? Right, because it's in the second row or the second period, correct? So lithium currently has 2 energy levels to work with. What can happen, though, you already know that lithium has 1 valence electron. How do you know that? Because it's in the first group, right? So we know lithium has 1 valence electron because it's in the first group. And that's because, group number establishes the valence number. So what lithium can do is lithium can lose that valence electron. What happens when lithium loses that valence electron? It literally loses the whole energy level. It's gone. So lithium is left over like this. So what happened to the size of the radius? Right, it decreased. So you decrease the atomic radius with cation formation. Cations meaning lithium 1+. You could do that with any of them. You could take calcium. How many valence electrons does calcium have? 2. If I lost my 2 valence electrons, I lose my totally valent shell, which would decrease my radius. So cations are always smaller than what they came from. And there's another, not only are we losing the energy level, but the fact that now you have more protons, now the fact that you have effectively more protons than you have electrons, because in this case we previously had 3 protons, 3 electrons, and then in this case we have still 3 protons, because we can never change our proton number, but we lost 1 electron, so therefore you have 2 electrons. Who's winning this war? Definitely the protons, which would cause the radius to shrink further because we're trying to have a higher attraction from the nucleus. So you need to know cations have a decreased atomic radius. Decreased, yeah. So what do you think is going to happen with anions? Right, increase. And that's because of something else. And I want to draw this one for you too. So anions, let's go with fluorine. Fluorine has 1s2. So it's 1s2, 2s2, 2p5. So how many valence electrons does fluorine have? Huh? What group is fluorine in? 7. Fluorine is group 7. So how many valences does it have? 7. And if you look at the electron configuration, can you see the 7? Yeah. Right, because you can see the 7 valences are from the second energy level, 2 plus 5. So 2 from this one and 5 from this one. Okay, so fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Okay, its general size is, generally 2 energy levels, so it's kind of small. But as I add, you see that it's 1 away from noble gases. It wants to be like neon, right? What's up? What's up?
I was asking whether it's valence electrons, only just basically the outermost.
So I always say very outside because valence electrons are the very outside. So the second energy level is the very outside energy level. Okay, so fluorine wants to be like neon. Fluorine is 1 away from neon. So fluorine is going to gain that electron. And as it gains that electron, I'm going to put it right here. Notice now that we have more electrons in the outer ring than we had before. What are those electrons now going to do with each other? Right, electrons repel each other. Previously they were okay, but when you shove 1 more electron in there, all the electrons kind of space out and they repel each other and they push away from each other. That repulsion causes the electron cloud to increase. So what's happening to the radius? It's bigger, right? And so I can say, I also talk about from the perspective of the effective nuclear charge, because previously fluorine had how many electrons? Total electrons. 9 total, because it's the ninth element over. So I previously had 9 protons and 9 electrons. But when I add 1 to make fluoride, the negative charge, it still has those 9 protons, but how many electrons? 10. So you can kind of see the electrons are winning, so they're going to space out because the protons cannot effectively attract all 10 electrons when there's only 9 protons. So you can talk about it from different perspectives, but I like the repulsion one because if you think repel, you think move away from each other, so the cloud gets larger. All right, so thumbs up if that makes sense. All right, so we got to work on some of the explanations here. Okay, I'm going to keep working on explanations part of it because I think after a couple more examples, this will make sense. Let me go straight to examples then. I'm skipping ionization energy for now. oops, yeah, here's the first example. This is what I have on your paper. Ready? So let's talk about aluminum and boron first. And let me make my periodic table a little bit bigger. So find aluminum and boron. Aluminum and boron. Throw up your right hand. Right hand radius. Who is larger? Aluminum. So are we going across the period or down a group? We're going down a group. So you should go down the group. So on your periodic table, you're probably going to be drawing this a lot. Go down a group. Aluminum is larger. Now you have to tell me why aluminum is larger. Any volunteers? Go for it.
Because it has more. I don't know.
All right, wait. Levi. Thank you. More energy levels. More energy levels because down the group. Good. That's the kind of explanation I'm looking for. Not because it's lower in the group. That's not enough. That's a simple statement. I want the explanation, which is more energy levels. Okay, so let's do sodium and aluminum. Sodium and aluminum. Here's aluminum. Here's sodium. Who's larger? Sodium. Okay, so why is sodium larger? Volunteers? Jack.
There's less protons.
Okay, so less protons yields what?
Larger than
Because lower. What am I looking for?
force.
What's that force called?
Attraction.
Zeph. Zeph? Lower effective nuclear charge. Same thing, less protons. I'm cool with that. But if you really want to be like the queen bee here, king bee, then you want to say lower effective nuclear charge.
Wait, I thought that if there are less protons,
The radius is larger.
the radius is smaller.
Less protons means less pull. Less pull means electrons are crazy and stay outside.
Because, like, for aluminum, you said that it has a bigger radius.
Mm-mm. I said versus boron. Aluminum versus boron, aluminum's larger.
But
Aluminum versus sodium, you have to consider the new scenario now. New scenario means sodium is larger.
so even if they have more protons, if it's in a lower period, then it has a smaller radius.
More protons, different period.
It's in a lower period than
Because
So you're considering
aluminum has more protons than barium.
boron, yeah.
Boron.
But that's what I said in the very, very beginning. When you're talking across a period, you talk about nuclear effective charge, and that's how you explain it. When you're going down a group, you totally ignore the protons, you totally ignore the effective nuclear charge, and you're concerned about energy levels, the shielding effect. Two different arguments for two different scenarios. That's why I want to do one of each. Okay, so keep those two separate. So does that make sense? You're keeping electron shielding, aka energy levels this way, and then Zeph this way. All right, let's go do ionization energy. Ionization energy. So basically you need to write down the definition first. The energy required to remove a valence electron. VE is valence electron. So the basis of pretty much every other trend, it's really helpful to know a lot about the atomic radius. That's why I kind of drill that a lot up front for like 20 minutes. So knowing a lot about the atomic radius will drastically influence your ability to do everything else. So that's where you have to hit that. So we're talking about ionization energy. It means what it says. The energy required to ionize something. When you want to ionize something, that means you're changing electrons. Specifically in this case, though, we're stealing electrons. We're taking electrons. So, like we were talking about earlier, nobody was going to steal Allie from me, but everybody could steal Tyler because he was so far away. So that's the electron debate we were just talking about. So valence electrons are the very outside shells. So if I'm talking between sodium, look over here on the board, versus argon, whose electron, valence shell electron, is easier to take? Why sodium? Why are you saying that?
Farther out.
It's farther away. So what are you kind of referencing here? You're referencing the atomic radius and Coulomb's law at the same time, right? Because you're saying the farther away the electron is, aka the larger the radius, the lesser the force of attraction between the two, the nucleus and the electron. The closer the nucleus is to the electron, the higher the force of attraction. So you just told me it was going to take less energy to take this one. So you need to equate less energy due to there's no force of attraction. This one's going to require more energy to take the electron because there's more force holding it closer. So forces and energy are going to be kind of intertwined here. All right, so fill in the blank for me. It takes less energy to remove an electron far from the nucleus. So like energy level 5 or something, or energy level 6, something far away from the nucleus. So these are always comparative. They're relative to other things that we talk about. We'll usually compare 2 or 3 together. So it's going to require more energy. I have to put forth a lot more force of an energy to take an electron from a what?
Higher period.
Not a higher, because higher period, I think higher energy level. So when you say higher in the periodic table, that's a lower period. I'll say a smaller period, or low energy level. I know what you're saying though, because low period, higher on the periodic table. All right, so it's going to take a lot more energy for me to take something from a smaller radius. So I'm going to also add to this what I just said. Less energy to remove an electron from far from the nucleus, which is a large atomic radius, and this will be more energy to remove an electron from a smaller atom or smaller atomic radius. All right, so those are very connected. And I'm going to go back to the picture you guys drew, and we're going to write down why. So the explanation why is referring to our 2 factors we talked about from slide 1. All right, so that means I'm going to flip back where we drew that. Yeah, okay, so ionization energy increases. I'm going to do this one in blue here, okay? Ionization energy increases up and increases to the right. Now you have to tell me why. Okay, let me see if I can make some space here. Let's do this. Increases up. And why, Levi, would the increase up a group?
Because it's like there's electrons at other groups. Like
And the I see what you're saying. So
there's since the valence electrons are the ones leaving, like farther out, they're the ones with the higher energy. So there's not as much to counter. You get what I'm saying?
I think I do. I'm going to put that in better words. So that the ionization energy, the energy required, is increasing up a group because, Nick, tack onto that. You're going to use your hand up.
Because the amount of valence electrons increases as you go down.
The number of valences are going to change
Right,
as you go
like
across.
the energy levels
Okay,
increase as you go down. So it would be
I see what you're saying.
okay. So you wouldn't need as much energy a higher up.
No, you would need a heck of a lot more energy higher up. Jack,
I mean, you'd need more to take it off.
Yes, okay.
Because there's because of the energy levels, there's less energy levels at the top, which makes it harder to pull away.
Okay, because of no electron shielding?
Yeah.
Reading your minds. Okay, electron shielding. So the whole 2 factors we were talking about at the very beginning. Less electron shielding up here means nucleus is very strong and very much attracts its own valence shell. So stronger, so lesser because lesser electron shielding at the top of the group. There's more electron shielding. Electron shielding at the bottom because there's more energy levels. So if you have a lot more electron shielding happening, the valence shell is weakly attracted to the nucleus, meaning you require very little energy to take that electron. The more electron shielding at the top, due to less energy levels, means that you're going to put forth a ton of energy to take that electron. That electron requires a lot of energy to take, whereas this one requires very little energy to take because it's so far away from the nucleus. So I keep explaining the same thing, but talking about different trends. Shielding effect on this one. And I'll go to the page if that helps, because I thought this would help if I try to explain it all in one, but I'm just going to try. Let me go back here for you. No, not this one. No. Nope, I don't explain it anywhere else. That's my explanation. I don't think I had anything else for you. Because these up here are smaller, so there's less shielding. These are larger, so there's more shielding. Okay, so that's the group trend there. That's down the group. So across the period, we said the ionization energy, the energy required to ionize something is going to increase. So why would the ionization energy be bigger over here and smaller over here? What factor? Right, so as you go across from left to right of the periodic table, there's a bigger energy, ionization energy, due to increased effective nuclear charge, because they have a tight hold on their electrons, whereas over here, lesser effective nuclear charge means they have a less tight hold on their electrons. So you require a lot of force to take these electrons because the nucleus is so attracted. Yeah.
So like with helium taking this
To take its electrons? Probably helium or neon, helium or neon. They're really close, but helium's got such a small atomic radius, tiny atomic radius. Yeah, that it's the valence shell is so close to the nucleus, you're practically never going to take its electrons. Neon's a little bit easier. Yeah, good job. So you see the trend is very much related to if you're talking about ionization energy, the highest ionization energy is farthest from the corner of your hand. It's over there at helium. So who's the largest radius? This way. Francium, right. The largest radius is going to be the one that's farthest away from the corner of your hand. Francium, lower left corner. Yeah? So you can see that the trend is very much true all the way down. All right, let's do... Oh, I think I have questions on this one. Hold on. Questions? Yes, okay. So let's do calcium versus zinc first. Lowest ionization energy. And I encourage you on your periodic tables to draw yourself your ionization energy trend. So who's lowest between calcium and zinc? Where's calcium? Here. Where's zinc? Here. Go for it, Levi. Calcium, why?
Because exposure there.
That's not a reason. Because
There's less electrons being showed.
But remember, when you're talking about across a period, you don't reference electrons. Anna's got your back. Less Zeph, thank you, because lower protons or lower effective nuclear charge, meaning the nucleus is not holding onto those electrons very strongly. So you don't have to go for like nearly as much energy to take them. Okay, let's do aluminum and tellurium. Where's tellurium? TE. Let me see TE. Okay. This one's a little harder. Aluminum, tellurium. These are not in the same group or the same period. Any guessers? Thoughts? Go for it, Kevin.
pretty sure it's going to be because
Why?
there's more electron levels, so it's going to be farther away from the nucleus than aluminum, which even though the Zeph is lower, there's still not much influence.
You're a beautiful person. That was awesome.
Thank you.
I'm not sure what I just did. I just circled aluminum. Okay, so tellurium, because I like that you referenced both. The more important feature of the atom is the energy level. Because yeah, you had one proton, big deal. Yeah, your Zeph is a little higher, but not crazy amounts. But when you had a whole new energy level, you're in a new ballgame. Because it's not just one proton making a difference, it's a whole new shielding effect or a whole new energy level. So the bigger impact is moving across groups than across a period. So because, this was talking about lower ionization, because many more energy levels causing electron shielding. And then you say, yes, you know, the Zeph is higher, but that is less important. That's basically what Kevin said, trying to simplify there a little bit. Does that make sense why the group is such a big deal? It's just, I mean, a huge increase in size based on, a huge increase in the energy levels, which is size, will make a bigger impact in that 1 or 2 extra protons that the atom has. All right, so ionization energy, we feel a little bit better about it. Okay, let's do EA. No, electronegativity. Electronegativity. Okay, this is the definition part, and then I'll explain some more. So electronegativity. Sharing electrons. Let's see. You guys probably know carbon dioxide. No, you probably don't know carbon dioxide. Water. Okay. And we'll stop because I'll do this last example here. Alright, so I do personify the atoms. They're my friends, so I try to give them some characteristics. So we're going to talk about greediness now. Okay, some atoms really need to take somebody else's electrons, but sometimes it's not a whole. You're not able to take another electron, but you're able to share it in a way that you kind of still get to hold it sometimes, but you gotta kind of have to share it with another atom. So that's called a covalent bond. That's all a covalent bond is. 2 atoms are bonded together so that they can share a set of electrons. Just because they both want them, so sometimes they have to share if they can't take it themselves. Because remember, if you take an electron, you make ions. That would be called an ionic bond. If you share electrons, that's a covalent bond. We'll get into that in the next unit. So, if you're talking about the attraction between 2 atoms, one of them is usually more greedy. And that's because between hydrogen and oxygen, it's 2 away from a noble gas electron configuration, yes? Or, yeah, 2 away, because oxygen is, boom, boom, 2 away from neon. So oxygen is actually more greedy, or wants, electrons. Hydrogen couldn't really care about its electrons too much. It's got 1 electron. It could bounce up another one to be like helium, but it's really tiny. It's really hard for it to gain electrons that much. So hydrogen is less interested in electrons, meaning that oxygen, in that war between them, they're sharing electrons, but it's almost like 5 days out of the week, the shared electrons. I'm gonna draw a little bond here. That's a covalent bond, okay? 5 times out of the week, these 2 electrons are closer to oxygen. 2 days out of the week, they're closer to hydrogen. It's just they're hanging out around oxygen more often because oxygen is more greedy for electrons. And that's basically what electronegativity is. So our general trend is up and to the left. So up and to the left. Why is the electronegativity increasing this way and this way? Tell me based on our factors we've been talking about this whole day so far. So as you go across, let's go from lithium to fluorine. Lithium to fluorine. Who has a higher electronegativity? Everybody. Fluorine, definitely. I mean, it's this farthest up and to the right, so that's definitely true. Why though? Factor. Kevin. Okay, so it's closer to being a noble gas, so it wants another electron. How is it able to acquire another electron though? What's so great about fluorine? Thank you. Higher effective nuclear charge, more protons. So it's able to effectively attract electrons just better. It's got more protons than lithium does. Plus, fluorine, you've seen this before. Fluorine is not fluorine, it's fluoride most of the time. It's got a negative charge because it's able to gain, or if it has to share, it will share electrons. All right, that's versus lithium. So let's go lithium versus rubidium. which is down its group. Who's higher in electronegativity? Definitely lithium. Lithium doesn't really necessarily want more electrons, but it's able to gain more electrons more often, or greed for more electrons more often than rubidium. Why? Lithium looks like this, 1, 2 energy levels. Rubidium is 5. Okay, there we go. So, why? Anna. Yes, less shielding. Simple, sweet. Okay, this one has more. This one has less shielding, so the nucleus attracts electrons very well. That's a little bit more detailed. So lithium can attract electrons very well, so its electronegativity is larger because it can attract them better. Rubidium's shielding is very high, so the nucleus essentially doesn't even know what an electron is because it's way out there. So it can't even attract. It cannot attract an electron very well. Yes.
So, 2 things. First of all, basically what I'm getting from this is, whenever the amount of nucleus charge is more positive, it has a higher negative attraction.
It can attract electrons and negative charge better. Yes.
Yeah.
That's what we use though as an explanation across a period though, because that's a controlled experiment. Because if you change 2 variables at once, it's harder to decide. Okay.
Across a period?
Yeah, from lithium to fluorine, not down a group from lithium to rubidium.
How do you determine when you're going to?
You are concerned about energy levels only, no protons. Don't even look at the protons.
So, energy levels are the number of orbits, right?
Yes.
Okay.
Yes.
And second of all of this is just, all of these terms are to explain.
The periodic trends.
Okay.
Okay, so basically this weekend, investigate periodic trends a little bit more. We're going to do electron affinity on Tuesday. But what I would think you should probably do is maybe start problem set 6. Problem set 6, you'll know 3/4 of it right now. You can probably figure out the rest of it, but as you do your reading guide, the reading guide has questions related to this on it. So I have that right here, maybe in a second. No, nope. Oh my gosh. Oh, there it is. I just saw it. Okay, reading guide 6, I'll leave it there just for now, but you'll notice at the very bottom, there's your trends, power ions, form, shielding effect, a little bit more. This information up here is just some basic stuff about the periodic table. We already learned a lot about it, and we are in unit 1, but you guys will have to do a bit more. So that's going to be due on Tuesday, but if you have some time, make sure that you start problem set 6. It's not due until Wednesday though, okay? So you still got time. And then your carbon fibers, your research and your product should already be decided. And if you've not been on my website to claim your prize, go to Honors Chem Homework. You have to log into your Cabarrus account, but when you scroll to Monday Night Homework, where we had some time in class to work on it, there's links here. Assignment document, that's the one I showed you in class. The website that has a lot of information about carbon fibers, and then your sign-up sheet is here. And the first table is for my first period, and then you guys are my second period, so you have a table down here, and 5 of you have signed up. So if you would like to claim something, then claim something, but that's on you. You can go to your phone right now if you have an idea and you want to claim it. I can go through the edit history. Do not change anybody else's, because I've already had to call somebody out for my first period for being dumb. So please make sure you claim, and don't forget, the instructions are for you to claim a product that a company makes. So you can use Audi. I'm not doing this, so you guys can use Audi if you want. And then your presentation method. So a lot of you are using advertisements because that's fun. Virtual demonstration or presentation would be like a Prezi. Yeah.
Is it a different car?
Yeah.
Like, what if somebody else has Audi?
Then choose a very particular car of Audi.
Well, what about can I use like another brand of car?
If your research suggests that they would benefit from using carbon fibers, yes. Tesla? Anybody? Yeah. Yeah, but I said put it on there. I emailed you back. Yeah, so make sure you access that, okay? I'll go ahead and put it. I got you. Volts. I was trying to put Beetle, but okay. Is it volts?
I'm like, okay.
Oh, volts. Is it still a Z? No.
VOLKSWAGE.
That doesn't look right. Volkswagen.
Yeah.
That doesn't look right to me. And then I don't know. What'd you say? What did you do? Okay, you fill that in. All right. You guys can, if you want to pop up here and do this. Let me stop videoing. Oh my gosh, am I still videoing? Yep.